I will like to give you the definition of polarization of a wave and talk a little bit about how it can be used in engineering applications and why it is important. But before we actually start giving the definition, I would like to stop for a moment on the concept of electromagnetic wave. As you may guess, this is something that I really like talking about. Electromagnetic wave is a kind of combination of electric and magnetic field at the same time. They exist together at the same time, and the changes in the one generate the other. Both electric and magnetic field are vector quantities, so they are described by vectors. Unlike scalar quantities, for which you can just define its value at some point in space, for the vector one you have to define the amplitude and direction. When a plane wave travels in a free space, which is the best scenario to start our discussion, the electric and magnetic field vectors are perpendicular to each other, and both of them are perpendicular to the direction of the wave propagation. The wave carries some electromagnetic energy, and its direction of propagation is also the direction of the power flow, which remains constant. But the direction of electric and magnetic field vectors may change, as well as their amplitudes. And here we are ready for the definition. The polarization of a wave is a figure traced by the tip of the arrow representing the electric field as a function of time, at a fixed point in space, as observed along the direction of propagation. As you can see, the definition is pretty long, so I will point out several things. The first, and maybe the main one, is that polarization is described by electric field vector. As we all know, there is also magnetic field, but we usually don't use it to define polarization. The second is that we observe electric field vector as a function of time, which actually makes sense because it's not constant, its amplitude and direction may change. And one more thing is that we need to observe the field along the direction of propagation according to the convention adopted by electrical engineers. I'm pointing this out because different people may define polarization in different ways. For example, optical engineers observe the wave not moving away from them as we do, but when the wave is traveling towards them. I don't know why, crazy people. In general, the figure traced by the electric field vector is an ellipse, and the polarization is called elliptical. However, in particular cases, it can be circular when the ellipse turns into a circle, or linear when the ellipse shrinks into a segment of a straight line. And both circular and linear polarizations are widely used in engineering applications. But why do we care about it? When and where it can be used? I will give you two examples. The first is about my favorite antennas. Interesting fact that the polarization term can be also applied to antenna. The polarization of antenna is just the polarization of the plane wave that is radiated by that antenna. Imagine you have a communication system with two antennas. The first one is transmitting some signal, the second one is receiving. To have an efficient communication, those antennas should have the same polarization. Otherwise, a lot of the signal power will be lost, and the system will not be efficient. So when you are designing an antenna, or if someone asks you to build a new antenna to existing communication system, the first question you need to ask and answer is what kind of polarization should be used. The other example is about non-destructive testing problem. Imagine we have some object or a structure, and electromagnetic wave can pass through this object. Sometimes the polarization of the wave that is coming out of this object is different from the polarization of the incident wave. And by measuring how much these two polarizations are different, we can conclude about the physical properties of this object. Or if there are any cracks or defects inside, we can find their location by examining where exactly the polarization is different. So as you see, in two of these examples, the concept of polarization is pretty useful, and if you want to work on such kind of problems, you need to be familiar with that. that was just two examples. There are much more of them in real engineering world. So I hope after this my short talk, you could not only just learn the definition of polarization, but also got the idea of how widely it can be used nowadays. That's it.